Okay, here's a video talking about quotient groups and homomorphisms. Okay, so let's think about a group G that's the set of matrices A, B, C with a 0 there, such that B is any real number, and then A and C are non-zero real numbers. Okay, so you remember that the determinant of this matrix would be AC minus B0, and this just makes sure that my determinant is non-zero. So I can multiply these and it's closed, and you can double check that that's a group if you'd like to. So that's the group that I'd like to deal with, and then I'd like to define this homomorphism. Define F from G to R star by F of ABC equals AC. Okay, so you believe that A times C is a non-zero number. This is essentially the function that would take the determinant of the matrix. Now, you could hopefully believe that this is indeed a homomorphism. Let's see how I do that. F is a homomorphism. If I picked two elements in G, F of ABC times XYZ, well, if you put those things together, let's see, I'm going to do the operations rather quickly, but I guess it's AX in that corner, AY plus BZ in that corner, and CZ there, and that's equal to AXCZ, and AXCZ is equal to, let's see, ACXZ by commutativity of real numbers under multiplication, and that, of course, is equal to F of ABC0, and that is equal to F of XYZ with a 0 there. Okay, so it's a homomorphism, it's surjective or onto. So let's see how we'd say that. If I let Y be an element of R star, can I come up with something that maps to it? How about F of Y0, 1? F of Y0, 1 maps to Y times 1, which is Y. So it's surjective. I map to everything. Now, remember, it's in Hungerford's book. It's theorem 8.16 that says if you have a homomorphism, then remember the kernel, K, is a normal subgroup. So what is the kernel? I usually denote that kernel of F. Well, that's the set. Let me just, since I'm writing a question, there we go. K is the set of matrices A, B, 0, C, such that, let's see, F of A, B, 0, C equals 0. Oops, 0 isn't the identity in R star, right? The identity in R star is 1. So that's the set of A, B, 0, C, such that, well, what's F of that? AC equals 1. So that's the set of things that look like A, B, A inverse 0. Okay, well, such that A is any non-zero real number and B is any real number. Okay, so anything of this form will map to the identity. Now, what does the first isomorphism theorem say is true because there's this surjective homomorphism. It says that we now know that G mod K is isomorphic to R star. Well, you might know what G was. G is the set of matrices like this. You might know what K is, right? But you might not know. Okay, so let's think about the set of right cosets. So every matrix that looks like K, adjoined by some entry A, B, C, 0, such that A, B, 0, C is in G. You might say, I've got no idea what that set is. Well, the first isomorphism theorem tells you this might look all well and good, but this essentially boils down to R star.